So yesterday we were looking at the idea of back titrations, and let's now do some examples. So the first example we're going to look at is from June 2012. So AS1 June 2012, and it's going to be question 13. So these back titration questions are often about the amount of calcium carbonate present in eggshells. And we can work out the percentage of calcium carbonate using a back titration. And it gives us some of the practical details about how the eggshells are reacted with excess dilute hydrochloric acid and then titrated with sodium hydroxide. We talked yesterday about what is actually happening here, about how we use an excess of hydrochloric acid in the first place to make sure that all the calcium carbonate reacts. But then it is actually the unreacted acid that I titrate against sodium hydroxide. So if I want to work out how much did react in the first place, I can calculate that at the end by working reacted equals the initial acid added minus the unreacted, which we work out from our titration with sodium hydroxide. But we'll get onto that in our calculation later. If we just do our initial questions, the introduction questions, firstly they ask you what is, to explain the term standard solution. Standard solution is a solution where you know the concentration. So it's basically a solution of known concentration. And that is the solution that always goes into your burette. The next part, the choice of indicator, is pretty straightforward. You've got hydrochloric acid, which is a strong acid. So strong acid versus sodium hydroxide, which is a strong base. So therefore, the easiest one to use is phenolphthalein. You can also use methyl orange, but phenolphthalein we are a little bit more familiar with. But for the end point, you need to think about what is in the conical flask, and please do think about this, otherwise you're throwing a mark away. So we just talked about standard solution, and if we look to the question, we can see that it tells us it's the sodium hydroxide that's standard. So that's going to go in the burette. So that's your sodium hydroxide. And then in your conical flask is going to go your hydrochloric acid. So the starting colour is whatever colour the indicator is in whatever is in the conical flask. So whatever's in the conical flask, the colour of the indicator in that is your starting colour. So what colour is phenolphthalein in hydrochloric acid? Well, it's going to be colourless. Your ending colour change, or ending colour, is going to be the colour that it is in whatever is in the burette, which is sodium hydroxide, and phenolphthalein is pink in alkali. So then the question moves on to the calculation part, and we're given a step-by-step method of what happens in this titration. And so sometimes it's helpful to draw a diagram of what's happening, and that helps you keep a track of your calculations also. So we're told initially that 10 grams of our crushed eggshells are weighed out and added to 100 centimetres cubed of 2 molar hydrochloric acid. So in our beaker we would have 10 grams of our eggshell, which contains some calcium carbonate, and we've got 100 centimetres cubed of 2 molar hydrochloric acid. Okay, so those react together. That's an excess of your hydrochloric acid. And the next step is that the resulting solution is transferred into a 250 volumetric flask and made up to the mark. So let's think about what I'm transferring here. I'm transferring into the volumetric flask my solution. But what does my solution contain? Well, some of the hydrochloric acid will have reacted with the calcium carbonate in the eggshell. So what I'm actually transferring is all of the solution, but it actually contains all the unreacted HCl. So all the unreacted HCl is going into that volumetric flask. Okay, so if I draw my volumetric flask, okay, so that's put in might be about here, and then it's made up to 250 centimetres cubed. Okay. Alright, then we are told that 25 centimetres cubed portions are titrated with sodium hydroxide. So what I'm doing is I'm taking 25 centimetres cubed, and remember this is still unreacted hydrochloric acid, and putting it in a conical flask. Okay, that is then titrated, just because we don't have much room, that is then titrated against your sodium hydroxide. And this is where your calculation will start. It always starts with the titer of your standard solution. Okay, so in here I've got my sodium hydroxide, and in here I've got my still unreacted HCl, but not all of it, just a 25 centimetres cubed portion of it. So from this titration I can start with my titer and get the number of moles of sodium hydroxide that I use. Okay, from the moles, if we work our way backwards now, because when sodium hydroxide and hydrochloric acid are reacted together, they're in a 1-to-1 ratio. So the number of moles of sodium hydroxide will equal the number of moles of hydrochloric acid that reacted. And remind ourselves of what's in that conical flask. That is the unreacted. So that's the moles of unreacted hydrochloric acid. But we only took a 25 out of 250 centimetres cubed portion, so it's a tenth of the unreacted hydrochloric acid moles. So to look at that again, when we're going for a number of moles of sodium hydroxide to the number of moles of unreacted hydrochloric acid, we're timesing by 1 because our ratio is just 1-to-1. But when we're going from our conical flask to our volumetric flask, we only took a 25 out of 250 centimetre cube portion, so we need to times that number by 10. Remember, this volumetric flask contains all the unreacted moles of HCl. Okay, once we have the number of moles of unreacted moles, if we're working back to what did react with the calcium carbonate, we can work out reacted moles is the number of moles we initially added, which we can calculate from the volume and concentration of our hydrochloric acid, minus the unreacted moles. That probably seems quite complicated, but what we're looking at really is once you've got your number of moles of sodium hydroxide, you're timesing by 1 to get the number of moles of hydrochloric acid in the conical flask. Then you're timesing by 10 because you only took a 25 out of 250 portion. And then to work out the number of moles of hydrochloric acid that did react, you're taking that away from the moles that you added initially. So once we've got an idea of that, we're ready to do our calculation. So again, when we're doing our calculation, we're starting almost over at the right hand side here with the number of moles of sodium hydroxide, and we're working our way backwards. That's why it's called back titration. So the first part asks us to calculate the number of moles of sodium hydroxide used in the titration. So we really get that from our average titer. So the average titer was found to be 18 centimetres cubed. We're going to be using the equation N equals CV. And remember, the sodium hydroxide is our standard solution. We know the concentration is 0.1 decimeter cubed. So concentration is 0.1 decimeter cubed, and the volume, remember we need to convert that to decimeters cubed, so it's 0.018. That gives you a number of moles of 0.0018 moles, or it might come up on your calculator as 1.8 times 10 to the minus 3. Okay, scrolling on down then, you're then asked to work out or calculate the number of moles of hydrochloric acid present in the 25 portion. That's the portion that was reacted in the titration with the sodium hydroxide. And if we go back up to our diagram here, we're at this stage here. Okay, and because our equation is in a 1-to-1 ratio, the number of moles of sodium hydroxide that we used is the same as the number of moles of hydrochloric acid. So that's just times by 1 essentially. And so that's 0.0018 moles. Just to write that underneath the equation, you have your hydrochloric acid, you're reacting it with sodium hydroxide and getting sodium chloride plus water. If I have 0.0018 moles of the sodium hydroxide, then I'm going to have the same number of moles of hydrochloric acid. Okay, next part of the question then is calculate the number of moles of hydrochloric acid present in the 250 volumetric flask. So really, here I'm just going from 25 to 250, so I need to times by 10. Scrolling back up to our diagram, that's this stage here. Okay, when we're going from our conical flask to what would have been present in the volumetric flask. So I times by 10 and I get 0.018 moles. Next part of the question asks you to calculate the number of moles of hydrochloric acid added to the crushed eggshells. This is referring to your initial moles. And if you go back to the question, you'll see that they used hydrochloric acid of a concentration of 2 moles per decimeter cubed, and they used 100 centimeters cubed, which is 0.1 decimeters cubed. That is equal to 0.2 moles. So that is the initial that you added, and remember that's in excess. We calculated in part 3 that we used the unreacted moles was 0.018. So we need to take those away to get the next part of the question, which looks at the reacted hydrochloric acid. So remember, your reacted is going to be the initial moles, which we calculated here, minus the unreacted moles, which we calculated in part 3 from the titration. So our initial moles are 0.2, the unreacted was 0.018 moles. That gets you a total of 0.182 moles. Okay, next part of the question, calculate the number of moles of calcium carbonate in the crushed eggshell. Well, we need to relate it back to our first equation, which was calcium carbonate plus 2 hydrochloric acid would give us calcium chloride plus water plus carbon dioxide. So if I have worked out that there were 0.182 moles of hydrochloric acid reacted, I want to bring that over to my calcium carbonate. You can see I have a 1-to-2 ratio, and so I need to half the number of moles. So even just for here, you could do the working out as your ratio 1-to-2. So I'm going to divide by 2, and that gives me a total of 0.091 moles of calcium carbonate. Next part is calculate the mass. How do we get from moles to mass? Well, we use the equation mass equals N times RFM. Number of moles is from the previous question, 0.091. RFM of calcium carbonate is an easy one, of 100. And that gets us a mass of 9.1 grams. And then finally, you calculate the percentage by mass of calcium carbonate. How we're going to work that out is we're going to use a very simple equation of mass of calcium carbonate, and that's what we work out from our experiment, that's the 9.1 grams here, over the mass of eggshells, and times 100%. So our mass of calcium carbonate from the previous part was 9.1. The mass that was initially added, if you go back to the question, was 10.0 grams. If we times that by 100%, we get 91.0%. And that's your final answer. The next example we're going to look at is from June 2009. If you want to maybe try it and then work through this video to see how you got on, or you can try it with me also. So it's question 13 and it's exactly the same reaction again, trying to work out the percentage of calcium carbonate in eggshells. So again, we're reacting the calcium carbonate with an excess of hydrochloric acid and then titrating the unreacted hydrochloric acid with standard sodium hydroxide. It's your standard sodium hydroxide. So this is your titration equation. And because it's the standard, it's going into the burette. So where we'll start our calculation is with the titer of sodium hydroxide. First part of the question asks for the equation for the reaction between calcium carbonate and hydrochloric acid. We've seen that in the last question. Calcium carbonate plus your hydrochloric acid gives you calcium chloride. You need to do your swap and drop and you get CaCl2 plus your water plus carbon dioxide. Remember, this is a metal carbonate, calcium carbonate reacting with acid, so you get a salt, water and carbon dioxide. To balance it, you need a 2 in front of your HCl. What is meant by standard solution? Again, we met that in the last question. It's a solution of known concentration. Okay, so same type of question, just different numbers, and the question is just, it starts in a slightly different place, and you're asked to kind of do 2 steps in one in this example, but we'll work through it now. Okay, so again, you've got your eggshell being added to the hydrochloric acid, and then once as much hydrochloric acid as needs to react has reacted, and then we make that up to 250 centimeters cubed, and then we take 1/10 of that and we titrate it against sodium hydroxide, so that's going to be the unreacted hydrochloric acid. Okay, this question starts with the moles of hydrochloric acid added to the eggshell. Where you see that being asked for, that's your initial moles. Okay, so I go to my concentration and volume of hydrochloric acid for that. So my concentration is 2 molar of hydrochloric acid. My volume is 20 centimeters cubed. So the number of moles of hydrochloric acid is equal to concentration times volume, which is 2 molar times 0.02, which is your volume of 20 centimeters cubed. And that's equal to 0.04 moles. Next part asks you for the moles of sodium hydroxide used. This is where we started in the last question, so don't get confused if they ask you in a slightly different order. It's just still the same principles here. So the moles of sodium hydroxide used, we're going to get that from the titer. So even make a wee note to yourself. First part was initial moles, this part's the titer, and if you have a diagram, that might help keep you in check. So it's going to get that from our titer. Our titer is 18.6 centimeters cubed. And our concentration of sodium hydroxide is 0.1. So if I do N equals CV, the concentration is 0.1. The titer is 18.6 centimeters cubed, which is equal to 0.0186 decimeters cubed, and that is equal to 0.00186 moles. Okay. Next part is the moles of hydrochloric acid in 250 centimeters cubed. This is really asking you to do 2 steps in one, so don't let that throw you. Just think, remember, we're going from our beaker where our eggshell's reacting with the hydrochloric acid. That goes into your volumetric flask. That's then put into your conical flask for the titration. Okay, so what it's asking me to do is go straight from whatever my titer is to the volumetric flask. So it's actually asking me to do 2 steps. Okay, so I have the number of moles of sodium hydroxide used is 0.00186, and I need to work my way all the way back to how many moles are in the volumetric flask. So let's work out first of all the moles of HCl in 25 centimeters cubed. That's basically your titration. Okay, to do that we need our titration equation, which is the hydrochloric acid titrated against sodium hydroxide, giving you sodium chloride plus water. We worked out that we had 0.00186 moles of our sodium hydroxide, so that means that reacted with, because it's a 1-to-1 ratio, 0.00186 moles of hydrochloric acid. That's in your 25 centimeters cubed portion though. And if we think here, we took 25 out of 250. So we need to times that number by 10. So that's the number of moles in 25 centimeters cubed. So in 250 centimeters cubed, it's 0.00186 times 10, which is 0.0186 moles in the 250. So that's just asking you to do two steps in once, but don't let it throw you. Work out the number of moles in your 25 centimeter cube portion and then scale it up to your volumetric flask. Okay, number of moles of hydrochloric acid reacting with the eggshell. This is us at the stage of working out how much reacted. And remember, we must use the equation reacted equals the initial moles added minus the unreacted. Okay, this is your initial moles and these are your unreacted moles. So try to get that in your head. The moles of hydrochloric acid that you work out from your titration, that's the unreacted. The moles that were added in the first place, they're your initial. So to work out the reacted, you need to subtract the two. So my initial is 0.04. My unreacted is 0.0186. And so the moles reacted are 0.0214 moles. Again, this next step is asking us to do two steps in one. It's asking us to get the mass of calcium carbonate, but in order to get the mass, I must get the moles first. So we're bringing it back to this equation of calcium carbonate, which is up at the top of your page. So I'm only going to write half the equation. Calcium carbonate plus 2 of your hydrochloric acid. And in these equations, this will always be the same ratio. So we worked out that our moles of reacted acid are 0.0214 moles. I need to work out the number of moles of calcium carbonate first. And we can see that that's a 2-to-1 ratio. So I need to divide that number by 2, which is 0.0107 moles. And from that then I can get my mass by using the equation mass equals N times RFM. Number of moles is 0.0107, RFM is 100, so my mass is 1.07 grams. And then finally your percentage is the mass of calcium carbonate over the mass of eggshells, just a simple percentage calculation, times by 100%. So that's 1.07. If you go back to the question, you'll see that they initially added 1.12 grams of our eggshell. Multiply that by 100%, and you'll see that we have 95.5%. Okay, so take it step by step. Try to think, what are they asking me for here? Is it the initial moles? Is it the reacted moles? Is it the unreacted moles? And work step by step. Maybe asked in a different order, but the principle behind them will always be the same. The next type of titration that we're going to look at is that where you're asked to determine the number of water of crystallization. So this time we're going to be working from January 2009, and again looking at question number 13. So in this example, and they'll all be very similar, we're looking to determine the number of water of crystallization of sodium carbonate in washing soda. And it's not a back titration, so it's just one equation we're working from. And the sodium carbonate, which is a base, is titrated against standard hydrochloric acid. So standard is the concentration we're going to know, so that's going to go in the burette, and that's where we're going to start with our titer. So again, here's that question coming up again. What is meant by the term standard solution is a solution of known concentration. Make sure you know that. A solution of known concentration. Okay, next part asks you for the equation for the reaction between sodium carbonate and excess hydrochloric acid. So sodium carbonate is Na2CO3. Once it's dissolved in water, it'll lose its water of crystallization, so we don't need to include that part. Plus your hydrochloric acid, HCl. Okay, again, you've got a metal carbonate reacting with an acid, so you're going to get a salt plus water plus carbon dioxide. Your salt is going to be sodium chloride, which is NaCl, plus water plus carbon dioxide. To balance that, I'm going to need 2 sodium chlorides, and therefore I'm going to need 2 hydrochloric acids. Okay, so ready to jump into the question then. We have got 2.8 grams of our washing soda crystals being made up to 250 centimetres cubed in a flask. So let's just draw a wee diagram of that very briefly. So we're dissolving our 2.8 grams in water, and then we are making that up to 250 centimetres cubed. So imagine yourself making up a standard solution. You dissolve a little bit, or dissolve it all in a little bit of water in a beaker, and then you put it into your volumetric flask. So your volumetric flask, the reason you rinse the beaker and everything is so that you get all your moles of sodium carbonate in there. We then make that up to 250 centimetres cubed. And then for our titration, we're going to take a 25 centimetre cubed portion and put it in our conical flask for our titration. That means when we work out how many moles are in our conical flask, that is 25 out of our 250. So working backwards, you're going to need to times by 10. So you're going 25 to 250. So that's times by 10. And then once we've worked out how many moles are in our volumetric flask, that's how many was in the original sample. So essentially you're timesing by 1. That's the number of moles in the original sample, because all of it was transferred into the volumetric flask. Okay, so the start of the question asks you the moles of hydrochloric acid used. Remember, it's your standard solution in the burette, so that's going to be your titer. Your titer is 22.4 centimetres cubed of 0.1 molar hydrochloric acid. So it's N equals CV, concentration is 0.1, volume is 0.0224 centimetres cubed. That gives us a number of moles of 0.00224 moles of hydrochloric acid. Then it asks us for the number of moles of sodium carbonate in 25 centimetres cubed. Well, for this you need to think what your titration equation is, which is written just above in part 2, A part 2. So I'm going to write out the first part of the equation just to get our balancing number ratio. So it's 1 mole of sodium carbonate reacting with 2 moles of hydrochloric acid. I've just worked out that I have 0.00224 moles of my hydrochloric acid. So if I want to work out how many moles of sodium carbonate, it's a ratio of 2 to 1. So I divide by 2 and I get 0.00112 moles of sodium carbonate in the 25 centimetres cubed. The next part asks for the moles of sodium carbonate present in the sample. Now go back to your diagram here. Remember, all of your moles are in the volumetric flask. So if I work out how many are in the volumetric flask, then I work out how many are in the sample. How do we get to the number that are in the volumetric flask? Well, as we discussed, our titration portion only has 25 out of 250, so we need to times that by 10. So we're timesing this by 10, and that gets us 0.0112 moles. So 25 centimetres cubed up to 250 centimetres cubed in your volumetric flask. That's why you're timesing by 10. Okay, and remember what's in the volumetric flask contains all the moles that was in the sample in the first place. So we can go straight from that number of moles to the mass of sodium carbonate in the sample. So we're going from moles to mass, so we're going to be using the equation mass equals N times RFM. Our number of moles is 0.0112. Our RFM of sodium carbonate is 106. That gives us a number of moles of 1.1872 grams. That's our number of moles of sodium carbonate. Remember, the formula of your hydrated sodium carbonate is with X moles of water. But what I've just worked out is the mass of this. So the rest of the mass of the sample was water. That's the rest of the 2.8 grams that was water. So if I want to work out the mass of water, then I just take that away from the original mass. So my original mass is 2.80. 1.1872 of that is my sodium carbonate, which means that 1.6128 grams is water. Next part asks me to work out the moles of water in the sample. They may not give you this step, but you do need to work out the number of moles of water in the sample, because then we will do a mole ratio to get your water of crystallization. So the moles of water is N equals mass over RFM. Mass of water is 1.6128. The RFM of water is 18. And that gives you a number of moles of 0.0896 moles. Okay, the reason I worked out that is now we're going to do an empirical formula type calculation. So what we've got now is the number of moles of sodium carbonate and our number of moles of water. So once we get the mole ratio, that'll tell us the formula. So I have worked out in this part that I have 0.0112 moles of my sodium carbonate, and I've just worked out that I have 0.0896 moles of water. Okay, when you're trying to get a mole ratio, what you do is divide by the smallest number. So divide by the smallest number, which is going to be this one, your moles of sodium carbonate. So I'm dividing both numbers by that. So essentially I'm doing 0.0112 over 0.0112, and I'm doing 0.0896 over 0.0112. Dividing both of those numbers, obviously you're going to get 1 for the number of moles of sodium carbonate, and the number of moles of water works out as 8. That tells us that the formula of sodium carbonate to X amount of waters is 1 to 8. So that means your value of X is 8. So your formula of your sodium carbonate is Na2CO3 dot 8 H2O.